Assalamualaikum warahmatullahi wabarakatuh. So this is example 2 from power electronics note. So this is the simple uncontrolled rectifier circuit using diode connected to the inductive load. And the information given is that it has a voltage sinusoidal 100 sine 100 sine 120 pi t. The load is R 80 ohms and also the L 50 millihenry. The extinction angle, which is beta, is given to 100. So determine the expression for the current in the circuit, expression for the average voltage, and expression for the RMS current. So on the expression, do not actually complete the answer, okay, just an expression. So from the information from the question, the information that we can extract is actually the omega, which is 120 pi, the voltage source, the extension angle, resistor value 80 ohm, and the reactance. So the reactance can be calculated by using omega L. So from the calculator, the omega L is actually 18.84 ohm. Okay, please be note this is actually J. Okay, there's an imaginary part here. Okay, so from here we can actually compute your impedance Z load, which is you can use your calculator, which is this one is 80 plus J 18.84, which is in rectangular in polar form is lab 82.2 angle 13.35 13.25 ohm. Okay, so and then theta is actually inverse tangent of the omega L over R, which is you can actually obtain as equals to, which is 13.25, which is similar to the actually angle of the impedance. Okay, so you need actually to calculate. Actually, I just want to verify the relationship between this theta. Okay, so theta is actually referring to the impedance angle. So once you have the impedance angle, then you don't need to calculate this one because it actually give you the same answer. Okay, and then next is actually the tau, the time constant tau, which is L over R. So you can compute this by 50 millihenry over 80 ohm, where the answer should be around 6.25 -4. Okay, so that is the time constant. So, and finally, I think we have complete all the information need to be inserted in the expression of the current. So the expression of the current, we may recall, is actually I omega t, which is Vm over Z sine omega t minus theta plus sine theta exponential negative omega t over omega tau. Okay, so Vm over Z, so we have 100, only take the magnitude, okay? This one also only take the magnitude. So 100 over the Z is 82.2, okay? Multiply with sine omega t, so theta is 13.25 degrees plus right now sine theta, so you need to have sine 13.25, which is will give you 0.23 exponential negative omega t. Sorry, omega is also given, so it's okay. We can actually, oh, okay, so the omega is given, so we just put it inside. So this one should be 120 pi t minus, okay. So this one also given. So you should use this. So negative 120 pi t over 120 pi multiplied with this one. So 100 multiply with pi multiply with 6.25 exponential negative 4. So this one is actually 0.24. Okay, also you can actually simplify this. So it will give you this one 1.216, okay, sine 150 omega minus 13.25 degrees plus 0.23 exponential. This one also 120 multiplied with pi, sorry, divided by 0.24. Okay, so it will give you 1,500. It's okay. I think you can just leave it like this. It is okay, still acceptable. Okay, so this is the answer. And for the expression, so very simple expression. So please, you need to know that for anything average function, okay, the average, you need to know the equation for the general average equations. So the general average equation is actually 1 over unit, is actually 1 over period, and then you need to integrate from 0 to t, the one period, and then just I. Okay, this is omega t actually. This one is also omega t. Okay, the omega t. Okay, so for the expression, so we know that the period is actually 1 over is actually 2 pi, so we need to actually integrate 0 to 2 pi with an expression of I omega t, which is 1.26 sine 120 minus 13.25 plus 0.25 exponential negative 120 divided. So this is actually the expression. Okay, and what about the RMS? So the RMS always IRMS. Okay, so it is square root of 1 over t, integration from 0 to t, and then the current is actually square. So this is actually the general equation. So we have the period is 2 pi, so and then integration from 0 to 2 pi, and the expression of the current, which is 1.216, okay, sine blah 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 square. Okay, so that's all for example 2. So it's quite straightforward question actually. Thank you very much. Okay, so we continue with the chapter 2, still chapter 2, uncontrolled half wave with R load. Okay, so from the previous slide, okay, the previous slide here, we can see that the current is discontinuous. Okay, the current here is actually discontinuous. So some application require that the current to be continuous, and also actually when you have a continuous current, meaning that the average value of the current is actually very high compared if you have discontinuous current. Okay, so how to actually to modify this current to be continuous? Okay, so the modification can be done by simply put the what you call the freewheeling diode, which is connected parallel with the load. So right now this is your load, so you need to connect the what you call the freewheeling diode, okay, FWD, across the load. Okay, so how can the current actually can be made continuous? Okay, so when during the first cycle, of the voltage source here, okay, polarity is like this. So the anode is much more positive compared to the cathode. So meaning that this diode is on, okay. And as you can see, the polarity of this is actually negative, but this is also negative, okay. So the anode is negative compared to cathode, so meaning that okay, so this is on, so this one also will be positive, so this one also positive. But as you can see here, the anode is negative, okay, so meaning that this is off, reverse bias during the first positive cycle, meaning that the current, okay, will flow, okay, the current will flow through the load, okay. So the inductor actually will be actually charging, okay, stored some energy from the positive cycle, okay. So when become negative cycle, sorry, when it is a negative cycle here like this, okay, the polarity is changed, okay, instead of this one, so this one will become negative and this one is positive. So as you can see here, this one anode is negative, so meaning that this one will actually off, turn off. So, and as you can see here, the polarity of the anode for the freewheeling diode is much positive compared to the cathode, so meaning that this one is on, okay. So when it is on, this inductor will actually discharge the energy through the freewheeling diode, okay, through the freewheeling diode. So that's why the current will actually, the current output here will keep continuing, okay. So from the first positive cycle, the current will flow to the D1, flow to the load with a complete circuit here, okay. And during the negative cycle where this D1 is off, D2 or the freewheeling diode will turn on, okay. So the energy stored in the inductor will actually discharge and discharge through this freewheeling diode, and IO is still flowing, okay. And as you can see also, the voltage output during the freewheeling diode here when turned on is actually similar to the voltage across this diode. So this diode, when it is turned on in ideal characteristic, is actually has a forward voltage drop equal to zero. So that's why we have zero output. Okay, so this is actually the circuit operations. So this is actually the result of the output voltage and also the output current. So without freewheeling diode, we will see that the voltage will be have like this, right? We have a positive cycle and some negative cycle should be like this, right? But okay, this is because the inductor actually force the diode to turn on. But in when we have a freewheeling diode, okay, so the current will actually, during the charging, the current will actually discharge through this, through the D2 or what you call the freewheeling diode. So during the first positive cycle, D1 will turn on, and for the next negative cycle, D2 will actually turn on, and this is actually the current actually discharging, okay. And since it's actually discharging and the voltage across the load is similar to the freewheeling diode voltage drop, which is equal to zero, so that's why we have a zero output here. And this is actually the current diode D1, so this is for D1, and this is actually for D2. So as you can see, for the positive cycle, D1 will actually take the current, while for the negative cycle, current D2 will actually take over the current. Okay, so I hope you understand on the freewheeling diode.